In this video, we're going to look at intramolecular aldol condensations. These are really important reactions because it's a good way of forming rings. And so, what do we need for the reaction? Well, we need a compound with two carbonyls, two aldehydes, two ketones, or one of each. This is one of each. And what we're going to do, of course, is form an enolate from one, allow it to attack the other carbonyl. And we're going to then eventually split out a mole of water, and we're going to end up with a conjugated carbonyl. So one of the problems with these reactions is when you first look at them, there always looks like there's a multitude of possible reactions you can do. Because like in this example, there's three different enolates you could form. You could form an enolate on either side of the ketone, or you could form the enolate from the aldehyde. Now, relative acidity might help you guide this a little bit, but ultimately, the most important thing is the stability of the final product. And the stability of the final product depends on a couple of things, one of which is ring size. We're always going to try to form 5 or 6 membered rings if we can. The other one is the number of substituents on the final double bond, because the more substituents on the final double bond, the more stable the product. And since these things are reversible, the molecules can go back and forth searching out that more stable product. So how do we get started? Well, let's first think about ring size. So if we form the enolate next to the aldehyde, how many carbons is it to the next carbonyls? It's, well, 1, 2, 3, 4. That would be a 4-membered ring. 4-membered rings are not very likely. So look at it the other direction. Here we have, if we're going to form an enolate here, it's 1, 2, 3, 4 carbons to that carbonyl. That doesn't sound very good. But what if we form the enolate over here on the methyl? 1, 2, 3, 4, 5, 6. A 6-membered ring. What could be better than a 6-membered ring? So let's form the enolate on this side. So we're going to simply form the enolate. Okay. Push the electrons out onto the carbonyl. Grab the magic arrow. And there's our enolate. Now we can do our cyclization. We bring those electrons back from the carbonyl, reach over, attack the carbon of the carbonyl, electrons onto the oxygen. Electrons onto the oxygen. There's our reaction arrow, and there's our cyclized product. Now, of course, this cyclized product is going to get protonated from the water. Okay, so we pick up proton from the water and form our protonated species. Get a full hydroxyl here, and this hydroxyl, of course, is subject to elimination because we have a very acidic hydrogen next to that carbonyl, and so we'll very easily do an E2 elimination. I mean, what this is actually doing, you're forming that anion which is delocalized out onto the carbonyl, but I'm kind of showing you a shortcut here. I'm not bothering to draw that. And here's our final product. So our final product is simply a nice 6-membered ring. This is our good old friend cyclohexenone, which we've used a lot in the class. So that's our first example. So let's do another. So now I've gone to a diketone. Now the diketone is going to be very much like the aldehyde and the ketone, but in this case, it's completely symmetrical molecules, so we only have to worry about 2 possible enolates. And again, we're simply going to count. Now, if you're going to look at just acidity, you could form the enolate here most readily, but count 1, 2, 3. That would give you a 3-membered ring. We're not going to form a 3-membered ring. What if we start the methyl? Form the enolate out here. 1, 2, 3, 4, 5. That's a 5-membered ring. 5s are much better than 3s. You always look for a 5 or a 6. So in this case, let's just do this again. I need a hydrogen. I'll put a hydrogen. We could actually obviously use either side here. That's not hydrogen, that's a methyl. So let's draw our initial enolate. Okay. And out onto the carbonyl. It didn't take. Guess I didn't click it. There's our enolate. Now let it attack the carbonyl. There we go. Need a reaction arrow. Again, I'm not very good at clicking today. What's wrong? Oh, my arrow's not long enough. There it goes. Got to have those arrows long enough to go down to the next divisions. You see the problem I had that too. I didn't have that long enough, so it didn't extend down into the next region. But now I got it right. So let me use that water molecule up here. Take a copy of it. And there we go. We've done our protonation. I messed up again. Click the arrow. Having trouble clicking that today. So there's our product suitable for ready for dehydration. And again, the dehydration is going to be come around. Uh-oh, I didn't draw my hydrogen, sorry. Got to draw the acidic hydrogen. Here's the acidic hydrogen. Now let me draw the arrow. So come around, grab that arrow. Let me draw out the enolate the way I'm supposed to this time. I was lazy last time, I didn't do it. So this will form the enolate. There's the enolate. Let me just center this. Make it a tad smaller so I have room. And of course now we're going to do an elimination. Coming down where we simply take those electrons, reform the carbonyl, move the double bond over, kick out the hydroxide, and this will give us our final product. Okay, so that's a good example. All right, well let's do one where it's a little more complicated. Let me just reload here. I got this molecule, but I want to make this. Let me make this a little bit more complicated. Let's see. I want to go back. I will let me make. I'm gonna make this. Okay, I want to. This is going to be a 6-membered ring. I'm putting the carbonyls one apart, but I want to show. So okay, so this is now a more complicated example. And how are we going to decide what the products are going to be here? Let me save this in case I screw it up. So in this case, again, we're going to count carbons because we can actually form now 4 different enolates, either side of this ketone, either side of this ketone. So if we count, for starting over here, 1, 2, 3, 4, 5, 6. That's a 6-membered ring. From here, 1, 2, 3, 4. That'd be a 4-membered ring. So we got to use this one. Or, of course, from the side over here, we could use 1, 2, 3, 4, 5, 6. We could use the methyl. So we could form an enolate here, or we could form an enolate there. So we have a choice between 2 different 6-membered rings or 2 different 4-membered rings. Well, we're definitely going to do the one of the 6-membered rings. And the question is, which one? Well, let's think about this a little bit. If we form the enolate here, and we come around and cyclize into that carbonyl, what we're going to get, of course, is eventually we'll get a double bond, and the double bond will have no substituents because the methyl will condense into the double bond. So let's just do this. I'm going to cheat and just draw the enolate. I'm leaving out a step. I'm starting with the enolate. So what would this do? It would go 1, 2, 3. And we would form this ring system. We do an elimination, we get a double bond there. But let's do it the other way. I'll copy the molecule. Okay, well, I'll copy the arrows too. I moved the wrong one, that's what I did. Let me get rid of those arrows. Anyway, so let me get rid of the charge there. and let's just arbitrarily form the enolate from that side. So now we're also going to get a 6-membered ring. Okay. And I need a reaction arrow. And let me borrow the hydroxide. Okay. And so we do this one. Now we have a new product, and if we do the dehydration, we're going to form a double bond here. So what we're comparing is a double bond here on that one, or a double bond here on that one. Well, the one on the bottom is better because this one, the double bond will have substituents on both carbons. This one, the double bond will only have substituents on one carbon. And the thing of it is, these things are all in equilibrium. So you're going to choose the one with the most substituents on the final double bond. So the choice will be this one down here. And of course, when that goes ahead and does the rest of the reaction, I'm going to be lazy here. I'm just going to copy this. I'm going to copy it if I press the right button. So what will the final product be? Well, this oxygen will be gone, and there'll be a double bond here. And I can ask Oscar to redraw that. And this will be your final product. So these things are a little bit difficult to figure out, but the overriding things are, well, there's two overriding things. One is ring size, and the other one is that you want the maximum number of substituents on your final double bond. So they're very useful reactions, and we can make a whole lot of interesting things from them. So have some fun with them.